today we continue our advanced array signal processing lectures, and we inside of this tensor-based signal processing, let's say, section. So let me switch to our pages first. So I gave you a main, let's say, article if you want to get more information about tensor decompositions and its applications. Also, what we have for tensor decompositions, for example, HOSVD, and canonical periodic decomposition, Tucker decomposition, parafactor, and etc. All these things inside of this article, and we know main notation things. So for if we use scalars, vectors, matrices, and tensors in our notebooks, they can be denoted like this one. And if we switch to some articles for tensors, we will see this calligraphic bold-faced X, and for matrices, for example, just bold X. All, of course, this one and this one, they are capital X. Then maybe it will be better if we go through slides. So we have this example on slide 10. Let me switch to the slides. So this one. From one hand, why we can or we need to use matrices. So in some examples, matrix equations are usually more compact. So it is a really nice and compact version of all these equations. And using these compact equations, we can, for example, find some new insights. But then why we need to use tensors? For example, if we assume this type of array, so it is 2D array, we have here 3 elements for x-axis and 4 elements for y-axis, and overall we have 12 elements in our array. So if we want to collect all this data as a matrix, we need to concatenate all these vectors to one big vector. But then if we collect all this data using tensors, you can see we will have this nice 3D tensor, where this thing is our array configuration, and here we have time snapshots. And for matrices, we have here time snapshots for the columns, let's say, yes, for the columns, and each column is the data of this array. Then here, if we assume matrices, we have columns and rows, or we can say as vertical and horizontal vectors. And if we assume tensors, we have 1-mode vectors, 2-mode vectors, and 3rd-mode vectors, which is vertical and horizontal as for matrices. And the third one, we call it as lateral, for example. Then here, the main idea of unfoldings. So you, for example, have this tensor, and you can represent it using matrices also. In this case, we need to use unfoldings. So here you can see 1st mode unfolding, 2nd mode unfolding, and 3rd mode unfolding. And here we use the forward ordering. So from one hand, we have forward ordering, and from our hand, we have reverse cyclical. In MATLAB, we use forward, so this one. And in some articles, you can find reverse cyclical, or this one was introduced by Del Tower. And today we will see in which cases, let's say, the difference between them. So, for example, then we use the product with unfoldings. So what is the main idea for forward ordering? So if you assume first mode unfolding, first you need to increase the values for the first one, then for the second one, and then for the third one. If you assume second mode unfolding, first you increase the second mode, then first mode, and then third mode. And for the third mode unfolding, first you increase third mode, these values, then first mode, and then second mode. So you keep very, let me show maybe. So for the first mode, we increase first this value, then second and third. For the second mode, we increase this value, then first and third. And for the last one, we increase this value because it is third mode, and then we increase first and second. And this one for reverse cyclical ordering. Okay, you can see reverse cycle, then forward ordering. Here we have some examples. Linearity things, and we end with N-mode product. Yes, we see what we have for N-mode product and how we can represent it using matrices. And here we have an example. If, for example, we have a tensor X of size 2 by 3 by 2, so 2 by 3 by 2, and we need to multiply this one with matrix U of size 3 by 2, and we multiply it using one mode product. Here you can see first we need to represent our matrix, our tensor X, as the first mode unfolding, so this one. Here we use forward ordering, because first we increase first order, then second order or second mode, this one, and then we go to the third mode, so from this part. And then we multiply it with matrix U, and after that we need to go back, so we have this new tensor Y, but this one is one mode unfolding. Then we need to use inverse unfolding, and we will get new tensor of size 3 by 3 by 2, and which is denoted as tensor Y. Then here are some examples of these products, and let's go to the new topic here. So, for example, you know what is the chronicle product. So, for example, we have two matrices A and B, and if we multiply matrix A chronicle product with B, you can see that we multiply all values of matrix B with the elements of matrix A. So you can see A11 times full matrix B, A to 1, full matrix B, and etc. And overall, if, for example, matrix A of size M by N and B is of size P by Q, new matrix will be of size M times P by N times Q. So we need to multiply first dimensions here, P, M and P, and second dimensions N and Q. And you can see this multiplication here. When we represent this unfolding with matrix X, with tensor X, which is equal to this multiplication. So, for example, we can, okay, let's see this example. Maybe, right. And let me check. So we have, great. So today is lecture 28. 2022, December 15th. And let's see what we have for this multiplication. So here, we compare it with matrix and with tensor. So, of course, we can use one mode and second mode product for the matrix because this one have two dimensions. And here you can see if we represent this one using just products, we will first write matrix A, then times Y times B transpose. Maybe let's see why we have this thing. So let me rewrite first. B. So let's write, for example, N-mode product. So first example here, matrices. So here we have matrix X, which is equal to the multiplication of matrix Y with matrices A and B using first mode and second mode products respectively. So first one, I write first mode product and then second mode product. And here, let me show the idea inside of these n-mode products. In this case, I need to show you the sizes of these matrices. So for example, let's say that matrix Y of size M1 by M2, for example. Let's say matrix A. Let me write, for example, N1 times M1, and for matrix B, N2 times M2. In this case, new matrix X will be of size N1 times N2. So N1 times N2. And let's see how this works just with multiplication of matrices. So without these n-mode products. In this case, matrix X is equal to the multiplication of A with matrix Y with B transpose. And now you will see what we have here. So for matrix A, we have N1 times M1. So the number of columns of A should be equal to the number of rows of Y. So we have this thing M1 times M2. And then the number of columns of Y should be equal to the number of rows of B. But here we have B transposed, and we will write M2 times N2. So you can see we have this M1 and M1 here, and here M2 and M2. And overall we'll have N1 times N2. And now let's try to extend this n-mode product for tensors. So let's write second point here. Tensors. So in this case, of course, in other hand, we can show X transposed, which is just this multiplication of matrices A, Y, and B transposed, but overall result should be with transpose sign or transpose operation. So first, let me write this multiplication for myself. Here we have matrix tensor X, which is equal to the multiplication of tensor Y with matrices A, B, and C using first mode, second mode, and third mode unfoldings, respectively. And you can see, instead of 2 cases, we will have 3 cases because we have tensor of size, tensor with 3 dimensions. And let's start with first mode unfolding. So x1 and A, Y, 1. Here we have this Kronecker product. So first, let's see this one example, and then I will show you this. You can see the general equation below. We will see what we have for forward ordering and for reverse cyclical ordering. So for tensors, we have tensor x, which is equal to the multiplication of tensor y with matrices A, B, and C, using first mode, second mode, and third mode products. So maybe let's do this thing as before. So here we will have a tensor of size M1 by M2 by M3. So for this matrix, the sizes of this matrix N1 times M1. This one is N2 times M2. And the last matrix C of size N3 times M3. And here, the resulting tensor X with sizes N1 times N2 times N3. And now let's see the same multiplication, but using unfoldings. So here we show the first mode unfolding of X, which is equal to the multiplication of A. So I will leave here some spaces to write all these sizes of matrices and unfoldings. Then first mode unfolding of Y. And the last thing here is the Kronecker product of matrix C with matrix B, and this thing with transpose sign. So let's start from right side, and then we will see what we have for the left side. So we already know that we'll have N1, N2, and N3, but how we get these things? So this matrix of size N1 times M1. Then the unfolding of tensor Y, so first mode unfolding, from the left side. So the number of rows will be equal to the size of the first dimension. And the size of the second dimension, in this case, will be M2 times M3. M2, M3. And what we have here. So we have N by M2 and N3 by M3. So when we multiply this C with B, we need to multiply this N3 with N2 and M2 with M3, or M3 with M2 will be better. So in this case, we have N3 by, or let's say N3 times N2. Sorry. Yes. N3 N2 by M3 and M2. It is inside of this matrix. But then we do this transposition thing. So we need to transpose this resulting multiplication, and we will have M3 by M2 times N3 by N2. So in this example, yes, it will be better to show that this multiplication here is, I think, M3 by M2. Because, so the idea is the same, but to keep this connection between Kronecker product and our unfolding fields. So you can see here we have same number of columns and number of rows. Here we have same number of columns and same number of rows. So overall, this unfolding of X will be of size N1 by N3 times N2. And then we need to go back using inverse unfolding, and we'll get our resulting tensor X. So maybe let's show the second mode and third mode without these sizes, and then we will see the main idea inside of inside of this general one, so this one. So let me check CA here and BA. So let's write the second mode unfolding. Is equal. Here we first write the second mode matrix, then the second mode unfolding of Y, and here we have Kronecker product of C with matrix A. Transpose. Ключи в 503.
У тебя ключи?
Пока что да.
Ладно. У меня зачет будет 421.
Ага.
Ну, я полагаю, что
сейчас
должен управиться.
А, хорошо, хорошо.
Часов, значит, 6.
Хорошо, хорошо.
Начну там 6:20, 6:15.
Угу.
Ты еще будешь, да?
Да. So this one, second mode unfolding, and let's end these N mode products with third mode unfolding, and then we can see the main idea of relationship here between these matrices with Kronecker products. So here we need to multiply matrix C with third mode unfolding of Y and with B Kronecker product A transpose. So first, I will give you this thing. So when we look to the ordering things. So first I show you how we choose the values, but also with green color, I show you what we have if we take the transpose of this forward ordering. And this one is used here in Kronecker products. So let's see. Using, maybe, let me show it here. And maybe I will use my pencil. So we have matrices A, B, and C. So when we show the first mode unfolding, first you write this thing, and then let's see. So we need to go in this way. But you can see that we have here first one, and here we have, let's say, the end of this value. So we need to go back to this point. Yes. So we put A here and go in this way. So it is C first, this one, and then B, so this one. If we assume second mode unfolding, so we put this value first here, and also we go in this way. So we first write down matrix C, and then we write matrix E. And the same thing, first we put matrix C here, then we go in this way, so we write matrix B, and then write matrix A. So everything is easy, yes? So you can see the main idea here. So you go just from the last one to the first one, and you need to remove the nth value to this first matrix. So this one, first mode, so we need to take first. This one, second mode, so we need to take the second. And this one is third mode, and we need to take third. And the rest values written from the back to the first value inside of this Kronecker product. And let's see the same thing for the general case here on our slide 29. So you can see we have this tensor X, we have this tensor Y, but now the sizes of these tensors, or let's say the dimension, it is n equal to n, nd tensor. And here, if we assume a general n-mode product, you need to write here the matrix M superscript n, then n-mode unfolding of tensor Y, and here you start with the last value, so mn, then m n minus 1, etc. Here you have m superscript n plus 1. Here you have then n minus 1, and between them you can see this point or this matrix is located here. And you go to the first matrix M superscript 1. And all this thing with transposing. And let's see the same thing. But yes, you can see these forward ordering things. But now let's see if we use reverse cyclical. So we have the same equations for matrices. So you can see A, B, and here you can, if we calculate the transpose X, you'll have B without transpose and these two with transpose n. But the main difference is in tensors. So this n-mode product for tensors. You can see now you write A, B, and C here as before, but the multiplication here inside of this Kronecker product with transposition. You can see that we start here with B, and So we use this type of ordering, and maybe so maybe let's write the same thing with pencil, and I will show you this one using this scheme. So for this one is forward ordering, and let's write the same thing using reverse cyclical. So I will do it as fast as possible. So just to show you the main differences between these two ordering types. So you can do this thing with me. So as you want. B chronicle product C transpose. So this one for first mode unfolding, then second mode unfolding. We will have the same relationship. So here we have C chronicle product A, and the last one, third mode unfolding. So here we write C, third mode unfolding of Y, and here we need switch A with B. Transpose. So for this one, for reverse cyclical ordering, reverse cyclical. Let me show what connection we will have here. And of course, for this forward ordering, we can show that this way is used for transposition. So this multiplication of the chronicle products. So let me add here transposition. And let's see what we have here. In this case, we will have this type of the ordering for transposition. And let's see the connection between our unfoldings and these matrices inside of the chronicle products. So let's go step by step. First, it is first mode unfolding. So you write this matrix A here, and then you go in this way and go back. So first value after A, it is B, then matrix C. And we have all these matrices in this equation. Okay, then let's go to the second mode unfolding. So we write matrix B here, and then we go in this way. So first we write matrix C because it is after B, and we need to go back and we write matrix A. So C and A. And the last one, we start with matrix C here. So then we need to go back to the first value, it is A, and then matrix B. And I think the main idea here to see, let me check. Okay. So in this case, of course, here we need to write one. For example, this matrix will be of size M1, and first we need to write M2 and then M3. So, for example, here, M1 times M2 and then M3. But if we use, for example, this forward ordering, we start with the last value. But here we will have, in this case, M3 by 1, M1, because we go first to the last value and then go back to the first value. But here we keep the same thing. So if you calculate the size of this unfolding, you will have M3 by M1 and M2. For example. Okay, so maybe let's give as some notes for this N-mode product the number of slides. So let me check which slides is 29 up to, let me check. So I think 32. So here let's add N-mode product and slides. $29 up to 32. Then what we can compare, or which parameters we can compare of the matrices and of the tensors. So for example, we can compare the ranks. So what is the rank of the tensor? So here, let's start with the rank of the matrix. So you know that the rank of the matrix is the number of linearly independent items. So you can write down column rank and row rank, and the rank, let's say, the overall rank will be the minimum value between these two ranks. But what for tensors? In this case, you can see that we have, let's say, one mode rank. It is number of linearly independent one mode vectors, and the same things for second mode and third mode. And overall, these all ranks are, let's say, can be different. So they are not equal. And in this case, N rank of X, so first mode rank, second mode rank, third mode rank, is less or equal to the size of this N mode dimension, or let's say nth dimension in this case. But for matrices, you have this great thing. And then let's go back to the same example with this tensor X, and you already can see this one mode rank, second mode rank, and third mode rank, and why this one is equal to 1. So you can see that the first row and second row, they are equal. And also you can see that here we have 5, 5, 3, 4, 4, 9, 9, etc. So they can be calculated. For example, this second one can be calculated as the first row divided by 5, and then we multiply it by 3, and we'll have this row. And the same thing for this counts, and the same things for the rest of the counts. But here we have ranks equal to 2 and 2, and you can see that it's correct in this case. So let's go to the first decomposition, which is called as higher order singular value decomposition. So you can see we have some basic knowledge about singular value decomposition, but now we need to extend it for the tensors. So from left side, let's start with the matrices. We have this matrix X, and we can represent it using singular value decomposition, which is equal to this unitary matrix U times matrix with singular values sigma times unitary matrix V with remission. Or if we use n-mode products, we can represent it in this way. And now what we have for tensors. You can see that from left side we have the same X, but this one is a tensor. We have the same unitary matrices here. If we look to this one-mode product or n-mode product, and instead of matrix sigma, we have matrix S, which is called as core tensor. And let's see how we calculate all these things. So first, we need to calculate the singular value decomposition for each mode. So first, you take this tensor X, and you calculate the singular value decomposition for the first mode unfolding. And you will have this unitary matrix 1, then singular values matrix 1, and matrix V1 with remission. Then the same thing for the second mode unfolding, and then for the third mode unfolding. And then we keep only these unitary matrices, so left unitary matrices, or left hand. And you can see how we calculate the core tensor in this case. So we take our original tensor X, and then we multiply it with Hermitian of this left-hand unitary matrices, and with the corresponding n-mode products. So if we use first mode unitary matrix, we need to multiply using first mode product, then second mode product, and third mode product. And let's see what we have in this case inside of each matrix. Of course, let's start with the case of matrices. This matrix X represented with unitary matrices U and V Hermitian, they are unitary, and we have this diagonal matrix with singular values. And of course, all these columns are orthogonal because we just have one value at points, let's say, I, so only in diagonal elements. And what we have for tensor case. So this tensor X, which is 3D tensor, can be represented using core tensor, which is multiplied with unitary matrices U1, U2, and U3 using first mode, second mode, and third mode products. In this case, these matrices are unitary matrices as before here, but this matrix S is full tensor. So here we have only, let's say, we have elements only on main diagonal, but here we have values in each point. And the main idea here, the connection between this core tensor and this matrix sigma, this one is all orthogonal and this one is also all orthogonal. And for example, if you take the n mode unfolding of S and multiply it with its Hermitian, you will get this n mode singular matrix times n mode singular matrix transposed. So this one, for example, first mode. So you will have here first mode and first mode, and you need to compute first mode unfolding in this case. And you can see the connection between these values. So for example, here you have a tensor of size 2 by 2 by 2. And then you find these unfoldings of X. They will be in this way. So we use here forward ordering, as I see. Yes, forward ordering. So this one as in MATLAB. Then you calculate singular well decomposition. So we have here U1, U2, U3, and also sigma 1, sigma 2, sigma 3, and V1, V2, and V3. And then, yes, here we show that U1 is equal to this thing, U2 this thing, U3 is this thing, and the singular values for each mode. So n mode singular values. What else? And of course, how we compute the core tensor. As before, we take our original matrix X, so this one, and we multiply with this thing with unitary matrices 1, 2, and 3, and of course with Hermitians. Okay. In this case, core tensor looks like this one, and we can say that we represent our tensor X using HO3D, so higher order singular value decomposition. Maybe let me see some, or let's write this type of decomposition, and for which purposes we can use this one. Let me see what we have here. HO3D. Okay. So let's write here HOSVD, or you can find it as ML SVD. So, what is HOSVD? So it is I will give this notation. So higher order singular value decomposition. So SVD, you know, and here we have this HOSVD. And for MLSVD, it is multilinear singular value decomposition. But I don't know multilinear. Maybe it is like this one. Multilinear singular value decomposition. ML. So, for example, we have tensor X, which is 3D tensor. So let's write tensor X, which is complex of size M1 by M2 by M3. So to find HOSVD, we need to calculate singular value decomposition for each unfolding. So if we assume first mode unfolding, we will have U superscript 1 times sigma superscript 1 times V superscript 1 Hermitian. So maybe let me check just for 5 seconds. Yes. So first mode unfolding, then second mode unfolding, V superscript 2 Hermitian, and the last one, first mode. U superscript 3 times sigma superscript 3 times V superscript 3 Hermitian. So this one is singular value decomposition of the first mode unfolding, same thing, but the second mode, and the same singular value decomposition, but for third mode. So let's stop at this point and let's see what we have for these matrices. So in this case, let's write the sizes of this third mode unfolding. First, we need to write the size of this n mode, which is third mode, then times let's use, for example, these sizes for forward ordering. It will be M2 by M1. In this case, can you give me the sizes of these matrices? So for U superscript 3, sigma superscript 3, and V superscript 3 finish. Huh? So maybe one tip here. Let's assume that this one is, if you try to find the relationship with single value decomposition, let's assume this one like not economy size, so the original SVD. So U, the size of matrix U in this case. So maybe guys, are you here? Check. So let's start with U3. Of course, the number of rows is M3 because the number of rows of X is M3. And the same thing we can write for V3 Hermitian, but the number of columns. So let's start here. Let's review in our mind how work this single value decomposition. So you get the square matrices for U and V, and between them you have this maybe square matrix or maybe rectangular matrix sigma. And in this case, U3 will be of size M3 by M3. This matrix V3 Hermitian is of size M2 by M1 and times M2 times M1. And between them you have this rectangular matrix of size M3 by M2 times M1. Or we can show it. I will show it just with Scratch. So the square matrix, then rectangular matrix, and then square matrix like this one. So like this one, and like this one. So this one is U3, this one is sigma 3, and this one is V3 Hermitian. And of course, the main values for this matrix sigma is only on its main diagonal here. Like this one. And of course, the same, let's say, the same shape of the matrices will be for second mode and first mode. Okay. Then let me indicate here with green color this unitary matrix U for the first mode unfolding. Then with red color the second mode unfolding, and let's say with blue color for third mode unfolding. Then let's write how we compute the chord tensor. In this case, chord tensor is denoted as tensor S, which is equal to the multiplication of tensor X, original tensor, with this unitary matrices 1, 2, and 3, using n-mode products. So first mode product with U superscript 1, second mode product with U superscript 2, and third mode product with U superscript 3. And let's use the same colors for the first one, which is green, for the second one, which is red. Sorry. That's not the end, of course. We can show, okay, with colors, but also we need to add here the Hermitian sign. So this one with Hermitian, this one with Hermitian, and this one also with Hermitian. And let's use this blue color here. And let's maybe indicate with yellow that here we have this Hermitian sign. Here with Hermitian sign, here, and also here. So this one is chord tensor. Which has the same sizes as tensor X, because you can see that we have the square matrices U with left hand left-handed unitary matrices. And let's show this main equation for HUSVD, which is equal to X. We can represent it using chord tensor, one mode product with U1, and here without Hermitian sign, then second mode product U2, and third mode product U3. So I put this equation into a box. And let's maybe indicate it with yellow color. So using background yellow color. 1, 2, 3, 1, 2, 3, yes, yes, U. Correct. Here with yellow color. And for example, let's write here, of course. This one is HOSVD. And just with pencil, I will show you the general equation. So for example, X, tensor X is equal to chord tensor, first mode of U1, second mode U2, then third mode, etc. And the last one will be, let's say, N. Okay, let's keep here N, and we multiply it with U superscript capital N. So this one is general equation for HUSVD, where tensor X is complex of size M1 by M2 by etc. The last one M subcapital N. So this one is general equation. What else? So maybe let's show that this unitary matrix is U. So for example, matrix U. Let me indicate here maybe. For this example of X, N is equal to 3. In this overall example, we have N equal to 3. And we have this property for unitary matrices. So unitary matrix U sub n, for example, if we compute the inverse of this matrix, it will be equal to its Hermitian. So that's why we use the Hermitian of these unitary matrices to compute core tensor S. And let's show that for our example, n is equal to 1, 2, and 3. And the last thing here, maybe let's show this. What if we take the unfolding of core tensor S and multiply it with its Hermitian? So here we have core tensor S unfolding of mode n. Then we multiply it with its Hermitian. S n mode unfolding Hermitian. This thing is equal to the multiplication of the n mode singular values with its transpose. N mode singular value with transpose. Sign here. Which is, of course, real. These matrices are real of size m, n sub n by capital M sub n. And of course, let's maybe show, so we show here the general shapes of matrix sigma. And here, instead of this rectangular matrix, we will have a square matrix. With values on its main diagonal. Which is of size m sub small n, m sub small n, like this one. So what else? This one is called as HOSVD. So you can see this thing is something like full singular value decomposition. So you keep all the sizes inside of this core tensor and inside of these unitary matrices. But then we have a Tucker compression, or we can call it as truncated HOSVD. So maybe let's first show this one, or maybe just write this thing. So this truncated HOSVD will be as economy size of the singular value decomposition, but for higher orders. So, okay, so maybe let's write the name of this decomposition as Tucker compression. Tucker compression. Or truncated HOSVD. So if you use just original HUSVD, you will get only the unitary matrices and singular values, or core tensor. So you get, let's say, some basic information with these singular vectors for each mode and singular values for each mode. But Tucker compression is used to reduce the noises in our tensors. So it is the main idea here as the economy size of the singular value decomposition. So if you, for example, assume a noisy case, you have the data, you have some additional noise, and if you go back to the singular value decomposition, you will see the differences inside of the singular values. So you have some signal subspace of these single values, then you have this big gap, and then the rest of the single values, which is the noise subspace. And you can say, okay, here I have the signal components, and the rest of the data is noisy, and you just truncate it. And here we have the same idea, but with some additional points. Because you need to think about the rank of the tensor. So I will give you here just main points for truncated HUSVD. But we will go inside of this thing maybe later, when we will see the rank of the tensors. What is the rank of a tensor? So, Tucker compression, which is based on HUSVD. So maybe let's write here these main points, and then we will continue after a short break. So this compression can be used to reduce. So this one reduces the noise. In the noisy cases. And it is equivalent to the economy size version of the singular value decomposition. So this one is equivalent to the economy size. Economy size version of the HUSVD. Maybe I will give you here just some small hints and tips, and then we will go back to this truncated HUSVD later. So let's look one more time to this decomposition. So using these singular value decompositions. So you can see that overall we can have very big rectangular matrix here. And also we need to keep in our mind that the sizes here, so for example, M1 M2 and M3 can be different. So for example, let's say just an example. This tensor X, let's say, for example, it's complex and of size, let's say 50, 60, and 80. Okay. Then you will have U1 of size 50 by 50, then U2, which is of size 60 by 60, and the last one, U3, which is of size 80 by 80. And in the same way, you will have sigma 1 of size 50 by this 60 times 80. It is 4,800. The second one, 60 times 4,000. And the last one is of size 80 by 3,000. And you can see that the main values will be only in 50 here, and the rest of the values, like 4,750 values, will be just some zeros because of this structure. So you have only values on its main diagonal, and the rest of the values is just zeros. And also here, and also here. But of course, you can see that overall we always only assume these values using U1, because the main idea to use U1, U2, and U3. And when we use truncated HOSVD, first idea, we can find overall the rank of X, or we can find the rank for each mode, here, here, and here. So for example, for this mode, we can have the rank equal to 10, for this one equal to 12, and for this one, for example, equal to 8. And here we have this main idea, what we need to use. From one side, we can use ranks for each mode, or we can use overall rank of X. So we will go back to this idea later, but now let's end here, and let's do this short break right now. So maybe let's do this one not 5 minutes, but 10 minutes. So we will continue after 10 minutes. Yes. Okay. Да, вот смотрите, как бы сама идея, вот мы разложили-то разложили. И нам, по сути, не важно, что вот здесь нули, потому что мы все равно, как ни крути, мы используем вот эти матрицы. Эту и эту. Но можно как раз попробовать, например, найти либо ранг для каждого для каждой размерности. То есть, например, здесь он может равняться 10. То есть мы посмотрим здесь все значения и увидим то, что сигнальная часть только содержит 10 значений. И мы можем, например, это сократить 50 на 10 взять. То есть мы лишнее просто выкинем. Здесь может быть, например, 12, здесь может быть 8. То есть вот с одной стороны можно подойти ранг для каждой размерности, с другой стороны можно подойти ранг всего тензоров. Да, и вот тут главная идея, как будет правильнее. Но, как я помню, обычно берут общий ранг, то есть там какой-то ранг D, и то есть у нас будет core tensor с размерами D на D на D. То есть у нас core tensor изначально, он же такого же размера, как X, и потом мы его сожмем, получается, до именно вот общего размера D на D на D. Где D – это вот приблизительный ранг наших данных.
Что-то 50 до 4750.
Ну вот здесь.
Я понимаю, от 50 это у нас сигнальное значение.
Да, а вот по сути остальные 4750 колонок – это просто нули.
Я думал,
Нет. Это вот я разделил, где у нас вообще есть информация в этих сингулярных значениях, и где у нас просто нули, по сути. Через порядки? А что вы имеете в виду под порядком? Линейно независимых? Ну да, вот как раз можно либо так подойти, то есть мы будем смотреть только на вот 50 элементов, 60 элементов, 80 элементов, и мы будем смотреть у каждого отдельно. То есть вот у нас 50 элементов здесь, 60 элементов здесь, 80 элементов здесь, и сигнальную часть каждого выделять. Либо вот уйти, например, от сингулярных значений к глобальным значениям и уже использовать глобальные. Вот, давайте скажем, общий ранг тензора. В таком случае мы перейдем.
Если мы даже делаем unfolding, вставляем тензор как матрицу,
Да.
то все равно считается.
Но когда мы считаем вот так, это по сути будут матрицы, но мы можем вернуться обратно в тензор. В этом. То есть мы, вот сама суть здесь, как таковая работа с тензором, она хороша тем, что мы сохраняем структуру данных. Но при этом вот просто так взять и посчитать их, грубо говоря, невозможно. Нам все равно приходится переходить вот в анфолдинге, да, матрицы, и уже работать с ними и возвращаться обратно. Но при этом сохраняя структуру. Вот.
Там, короче, такая была картинка, то что даже если мы завышали порядок, то на спектрограмме, ну, например, где просто заведены порядка номера, амплитуды, и сами амплитуды. Нет, то в другом дело. При шуме они очень чувствительны. И
Можно сделать отбор.
чтобы нивелировать влияние шума, можно завышать порядок. То есть делать более сложную систему уравнений. Вот. А при этом как бы, нам все равно как-то нужно учитывать то, что мы определили порядок. Вот. И это можно сделать так, что вот после того, как тебе про ней разложил это все, ты для, условно говоря, установления сигнала или построения спектрограммы берешь только то количество доминантных значений амплитуд, которые тебе вычислил определитель порядка. То есть не все там, например, завышенный порядок, а только то, что ты определил.
Порядок это есть количество спектрограмм. Ну, количество,
Да.
число порядка, количество.
Но просто когда ты завышаешь порядок, у тебя там типа искусственно на выходе гораздо больше палок в спектрограмме получается. А ты, получается, берешь доминантные в том количестве, в котором у тебя определился порядок изначально. Вот такой у меня алгоритм. Я типа буду из... Ну, в этом деле окейки мне будет вычислять только циферку порядка. Вот. Они будут считаться с завышенным порядком, беря порядок половины от количества отчетов, такой предел. И вот он будет.
А ты будешь строить что-то амплитудное вот в этом порядке, что ли?
Но вот на выходе он же мне дает массивы, типа массив амплитуды, массив фазы, затухания, частоты. Вот, и у каждого типа массиве у них типа есть номера. То есть, соответственно, если я там, например, возьму, начну строить массив амплитуды, массив частоты, получу спектр просто. Вот, и когда я буду фильтровать массив амплитуд на доминантные, я буду записывать их номера, тем самым выделяя нужные мне, так сказать, палочки. Номера доминантных значений амплитуд. И в том количестве, в котором я определился порядок в деле дейки. Он просто будет завышен.
Завышен на половину от количества
Количество половины отчетов.
А что сколько?
Там, блядь, вплоть до 125. Количество отчетов 250 у меня вообще текущий исполнитель.
Вот, да. Я просто и думаю, у меня вот 200 отчетов.
Знаешь, в оригинальной статье, которую я изучал, там вообще они там считают 1024 отчетов, и тоже порядок у них, они брали там 512.
А если это город добавить слишком много шума?
Нет,
А ты не рассматривал, типа там?
не, мы смотрели с ним, то, что вот, например, такой-то SNR у нас, вот, берем такой-то порядок, потом завышаем, результат становится лучше. Просто это длительность вычисления увеличивается, то есть сложность решения уравнений и количество. А еще выборного тоже, когда там T-question рассматривал, ну, некоторые выводы для себя сделал. Там это близкая проблема утечки спектра. У него там такой код, то что окно Фурье он задал 100 секунд. Вот T-question, у него там написано 0,9. А это, короче, T-question это длительность сигнала. То есть вот это вот, по сути, все остальное он просто дополняет нулями, чтобы повысить спектральное разрешение. Типа, насколько точно ты можешь определить частоты. Но это искусственная херня, потому что если у тебя длительность сигнала маленькая, то у тебя спектр размывает. Ты просто дополняя нулями, получаешь более четкую картину из-за того, как у тебя размывает спектр. Так что чем больше длительность сигнала, тем больше реально различаешь способность при определении Фурье. Там типа Например, если сигнал ровно 1 секунду, ты разрешаешь способность 1 Гц.
Я много американских подкастеров с шоров появляется. В Ютубе. Так. Моим чувак рассказывал. На Милянке в детстве там нажался чувак с вторым говном. Там 70 лет, кажется, там если сейчас я трансляцию дистанции.
What is going on here?
Он сказал, что через неделю, когда меня увидит, новая статья про игру, что
Может, я только ладно дарю.
я не додумался, короче, через кстати, у меня там 3-4 типа компиляции останавливать и исходно смотреть, насколько там компонентов от народа зависит и от порядка. У меня там 4 таких цикла. И вот надо было функцию, хотя я сделал 4 рамки.
Да.
Дальше я запихну все это в один, но хотя бы комментировать, наверное, можно будет.
So let's continue. As I said before, we can find different ranks for each mode. So for example, here we can have, let's say, 12, 14, for example, 8, it is the ranks for each unfolding. But usually we use one rank equal to D, which will be rank of overall tensor X. But for this one, we'll go back later, I think, because we need to get what we have for these ranks first. So okay. So we have this singular value decomposition for each unfolding, how we see or represent it visually, and one example. Okay. And here, let's see what we have for order product and rank 1 product. First, of course, let's start with matrices. So, for example, if we assume two vectors A and B of size m1 times 1 and m2 times 1, respectively. Here, for example, we can write matrix X, which is equal to this column vector A times the transposition of this column vector B. Or we can see it in the following way. So we multiply all values of A, this column A, with value B1, then all values of A with B2, and etc. And the last one, all values of A with B sub M2. Or we can see it in visual way, like this one. And here, the main idea here that this X contains all pairwise product between the elements of the vector A and B. So this one is B linearity. And the same thing we can show for the tensors, but here we also add the third mode vector, C, with sizes m3 times 1. And we will have this outer product of these three vectors, and this one will be tree linearity, and maybe so this one I think will go to the single value decomposition. So maybe let's write canonical polyadic decomposition, and let me check. I will give you main information. So yes, why we use HOSVD first? We calculate these unitary matrices, then we want to use Tanker compression. Why? Because we want to reduce the noises. So first we calculate HOSVD, then we use truncation of this HOSVD and find, let's say, the approximation of this tensor without noises, something like this one. And then this new noiseless tensor, we can use this tensor to analyze. And in this case, to analyze, we need to use, for example, canonical periodic decomposition. So this HOSVD and truncated HOSVD to reduce noise, CPD to analyze data. So let me first write here canonical periodic decomposition, or CPD. So CPD. So this one is, I will write it here, canonical, polyadic, decomposition. So C, P, and G. Also, you can find this type of a decomposition as candecomp. So it is candecomp. Let me check. Or parafac. Canonical decomposition or parallel factors decomposition. So something like candecomp or also parafac. So this one for canonical decomposition, and this one for parallel factors decomposition, something like this one, parafac. And let's start maybe with this bilinearity, and or maybe we can start with trilinearity. But first, maybe, as I remember, let me give you the main slides for HSVD. So for HSVD, here we have some duplicated slides. So just okay. So here you can see. Let me check one more time. So here, 36. To this one, and then we have here duplicated slides. So 43. So for HSVD or MLSVD, we have slides 36 up to 43. And then let's go to CPD. So first, let's start, okay, with bilinearity, and then let's go to trilinearity to see all these things step by step. Bilinearity. So here we assume two vectors, A and B. A of size M1 times 1, and B of size M2 by 1. So two column vectors. And then, for example, we can calculate matrix X as the product of these two vectors. So x is equal to A times B transpose. So maybe let me show this one in detail way. So we have here elements A1, then A2, up to A capital M1, times B1, then B2, up to B M capital M2. So you can see we multiply A1 with B1, A1 with B2, A1 with etc. up to B capital M2. And the same thing, A2 with B1, A2 with B2, etc. And the last one, A M1 with B1, A M1 with B2, up to the last value of B. So it is just this column times B, this column times B2, and etc. So we can say this thing is equal to A times B1, then A times B2, etc. A times B subcapital M2 in this way. So this B linearity. And now let's extend it, this idea, to tree linearity. And maybe one more thing here about the rank. So you can see, in this case, we can say that X has matrix rank equal to 1. So why like this one? Because we have only one set of the columns. So we can say that this one is one set of columns. So we have only A times B. For example, if we have, this one. So we can call these two columns as one set. So A times B transpose. For example, if we have A times B transpose plus C times D transpose, this one will be X with rank 2, because we have the sum of two multiplications. If we add, for example, plus E times F transpose and etc., we will have rank 3. But the main idea here also that these A, C, and E, they are linearly independent, and also B, D, and F, they are also linearly independent. Only in this case we'll have rank 3 in this case. Okay, now let's write this. X has matrix rank 1. Maybe, okay, rank X has matrix rank 1. In this case, X has matrix rank equal to 1. And now let's go to tree linearity. What we'll have if we add third vector here. Оставь просто на столе. Tree linearity. So as before, we have matrices A and B. A of size M1 times 1, B of size M2 by 1. And now we add the third vector, C of size M3 times 1. And maybe also will be good if we add here that X is complex of size M1 by M2 using this multiplication. So X is complex matrix of size M1 by M2. And now, instead of matrix, we will have a tensor X which is equal to outer product of A with B with C. And let me check. Yes, outer product of all these vectors. And now, how we can represent this outer product? We can do it in the same way as here. So, for example, let's let me think how it will be better to show. So let's start, for example, with multiplication of A and B. So this outer product of A and B. In this case, let's indicate this one as, for example, x1. Maybe okay, let's use just x, maybe. So this outer product can be represented as x, which is equal to A times B transpose, like this one. So you will have the same matrix X, like here. Okay? But now, the main idea that here, I will continue with pencil, I think. We will have the collection of these matrices X multiplied with value C1, C2, up to C capital M3. So this thing's something like, let me show, here we have a slice. And maybe I will show C as the constant, the first value, so C1 times X, then this second slice is C2 matrix X, then etc. And you have the last slice, this one, which is equal to C subcapital M3 times X. So you can see we use the same idea, but now we need to concatenate, or not concatenate. When we say when we say concatenate, we mean we collect all these things to one matrix. In this case, it is something like to collect these new matrices to one tensor. And now, what we have in this case? So this matrix X of size M1 times M2. So this slice of size M1 times M2, this slice of size M1 times M2, and etc. up to this one. So overall, the size of this tensor X will be M1 by M2 by M3. Now you can see what we have inside of this outer product also. And this type of multiplication is called, or this one has a property called as trilinearity. So let me switch to the slide, which means as follows. So this tensor X contains all products between the elements of the vectors A and B and C. So this AI, BJ, and CK, we have trilinearity. And as before, so you can see we have, let's say, only one set of these vectors, A, B, and C. If we add here plus some another matrices A2, B2, C2, we will have a tensor rank equal to 2. As here, if we add another multiplication with linearly independent vectors. And if you increase, for example, here, the summation of these outer products up to 4, for example, you will have tensor rank equal to 4. But now, let's write here just for this X, but it has tensor rank equal to 1. So tensor X has tensor rank equal to 1. Now we will see that the tensor rank can be greater than 1, and we will see some examples on our slides. Okay. So on the top, we have an example with matrices, and on the bottom, we have the same thing, but for the tensor. So let's start with the matrices. Here we have a matrix of size 5 by 4. We calculate singular value decomposition of it. So we have U times S times V Hermitian. And you can see that we can represent this thing using summation of these unitary vectors times singular values here, 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 and here. So this one is called as sum of rank 1 matrices. And for this case, we will have rank equal to 4. Because if you remember, these unitary matrices, they are orthogonal. Yes. the columns of these matrices are orthogonal to each other. So in this case, this one is equal to matrix rank 4. And here we have the same idea. So the outer product of A1, B1, C1 plus outer product of A2, B2, C2, and etc. In this case, the tensor rank will be equal to 3. But so what here? Also, we call this type of representation of our tensor as sum of rank 1 tensors. And what here? We need to say that there is no direct relationship between these n ranks and the tensor rank. Yes, and I think we will go to the ranks after this canonical polyadic decomposition. So let's go next. Then we can, for example, collect this A2, A1, A2, A3 to one matrix, then B1, B2, B3 to one big matrix B, and C1, C2, C3 to another matrix C. So here you can see how we collect it. And in this case, we can represent this multiplication using n mode products. So here you can see first mode, second mode, and third mode products. And we need to multiply, in this case, the super diagonal tensor. It is the same thing as identity matrix, but for, in this case, for 3D case. So here we will have zeros for each value, but the main diagonal, but we can say main body diagonal, I think, main body diagonal will have ones in this case. Let's go next. Yeah, this one. Canonical decomposition, which is candecomp or parallel factor analysis or parafac, and also canonical periodic decomposition or CPD or CP decomposition. And here we can compare it also with singular value decomposition as before. So from left side, SPD of matrix, from right side, canonical periodic decomposition of a tensor. So here, as before, U and V is unitary. We can call S as core matrix. We usually call it as matrix with single values, and it is diagonal. And here, the main connection between these two representations, that here we have this super diagonal thing instead of just diagonal, and here we see that A, B, and C is not unitary in this case, if we compare it with matrices U and V. And then you can see two different equations for, of course, you can see that we have maybe the same representation, or we can say see what we have for these ranks later. Let's start with matrices. So if we compute the rank of matrix X, it is less or equal to the minimum size of our dimensions. So M1 or M2. And the same thing we can write for rank of X. So we need to multiply, okay, not the same thing. This one is less or equal to the product of n ranks. So when we compute unfoldings and find each rank for each unfolding, or we can go using the sizes of tensor X. So this one is less or equal to the minimum between this M1 times M2, M2 times M3, and M3 times M1. So maybe let's write this figure. And also, we need to write the main equation for canonical polyadic decomposition. It is this superdiagonal matrix times A times B times C using n-mode product. And also, I will give you an information. What does it mean with I, tensor I, sub 3D, small d. So, what we have here. As before, we have matrix X where n is equal to 3. So that means let's maybe start with the same thing here. So X, as an example, is the sum of outer products A1 with B1 with C1 plus outer product of A2, B2, and C2. And the last outer product is A3, B3, and C3, for example. Then we can represent this tensor in the following way. So tensor X is equal to the multiplication of a superdiagonal matrix I, which has 3 dimensions with size D, and this one is multiplied with A, matrix A, matrix B, and matrix C using first mode, second mode, and third mode product respectively. So I will let me check. Okay, let's put first this equation into the box. Then I will give you an information about matrices A, B, and C. And then also the size of this superdiagonal matrix. So this one is canonical polyadic decomposition. Where matrices A, B, and C is the collection of these vectors A1, B1, A1, A2, A3, then B1, B2, B3, and C1, C2, C3. So matrix A is equal to A1, A2, A3, So it is of size M1 by 3. Then matrix P is B1, then B2 and B3, which is of size M2 by 3. And the last one, C, it is C1, C2, and C3 of size M3 times 3. But in general case, so here the second size will be D. Let me show that D in this case equal to 3. And that's why we show here that this identity matrix of size D. So in general case, this identity matrix is of size. So this one shows the dimension. So for example, if we have 4D tensor, here we need to write 4 instead of 3, for example. So this one is equal to D times D times D. And this one shows the size of these dimensions. So this superdiagonal tensor is always a cube. So it is not a square matrix if we compare with square matrices. This one is a cube tensor in this case. And in general, if we assume matrix A, this one of size M1 times D, B of size M2 times D, and C of size M3 times D in general case. Next. What is next? Yes, here you can see the visualization of this superdiagonal tensor. In this case, it is, I think, D is equal to 4. So you can see 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And this superdiagonal matrix has 3 dimensions. So first dimension, let me check. First dimension, second dimension, and third dimension. And here you can see that it has only once on its main body diagonal, here, 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 here. And the rest of the elements with gray color, they equal to 0. Now, about the ranks of tensors. Maybe check here what we have. We have no information about ranks, yes. And now here, maybe let's show here the short information with ranks for CPD. That rank of X is the product of n rank, or we can show this one with minimum. if we look to the rank of x, it is less or equal to the product of here n rank of, sorry, here we have a tensor, and here also a tensor. Where this value n goes from 1 up to, let's say, capital N. So from maybe also show that this one is not minus, but it is n rank. Maybe let's add here n rank of x is n mod rank. So n mod rank. So from one side we have this connection with n mod rank, and from our side we can say that rank of x, rank of tensor x, is less or equal, and here we have the minimum value between these products. So the first size with the second size, then the second size with third size, and the third size times the third size. Like this one. So you can see from this one, for example, let's go back, or let me, okay, no, let's go back, just show here with a pencil. For example, we have tensor x of size, let's say 2, 5, and 4. And in the same way, let's say that matrix X is of size 2 by 5. So for the matrix case, we can easily say that rank can be only 2, because the minimum between them is 2. So here, the rank of X is 2, because it is the minimum between 2 and 5. Which is really easy. Now, what if we assume the rank, oh, sorry, the rank of tensor X or maybe let's say not equal, but less or equal. It is the maximum value of the rank. And what is the maximum value of the rank of X? Let's, for example, use, in this case, the second equation. So it will be the rank of x, and we need to compare 3 different values. So it is 2 by 5, it is 10. Then 5 by 4, it is 12. Oh, sorry, 20. And the last one, it is 2 by 4. So it is 8. So you can see that in this case, if, for example, the smallest dimension is equal to 2, but overall the rank of x can be 8. So we need to keep in mind that the rank of x can be bigger than the smallest size of the tensor. And this thing we will see in the following slides. First, maybe let's show the main slides for canonical polyadic. Let me check. So maybe let's show here what we have. This one for ranks, and we start with 44 up to 49. And one more thing here, slide 55. Yes. We'll leave also this one. 55. So let's first write the slides for CPD. So for this one, we have slides 44 up to 49. And one slide, for example, 55. Slides 44, 49, and slide 55. Let's go to these ranks. Okay. Let's start with maximal rank. So maximal rank means the maximum possible rank, which is okay. This rank can exceed all dimensions, and here we assume that our first dimension is constant and equal to 2, and we change the values m2 and m3, and we see what we have for the maximal rank with this variable m2 and m3. And as red color, you can see maximal rank, which will be bigger than maximal number, for example, for m1, m2, and m3. So, for example, if we assume the smallest tensor 2 by 2, the maximal rank can be equal to 3 in this case. And here, this example with 2 by 8 by 8, the maximal rank will be equal to 12, but the smallest dimension is equal to 2, and also these two dimensions also smaller than 12. So this one for maximal rank. And typical rank or generic one. So maybe I will give you just the main idea here, that it is equal to this one. So here you can see we choose, for example, here m by 2. And in this case, typical rank will be m and m plus 1. So this one. This one is, for this m, we need to choose, how to say it, the largest dimension. Because if you look to these examples, here 2 by 2 by 2, or 3 by 3 by 2, or 5 by 3 by 3, we always choose the biggest value or largest value. So here 2, here it is 3, here it is 5. And we also plus 1 here, plus 1 here, and plus 1 here. And the same thing here. But what we have here, it is m by n, and m is greater or equal to 2n in this case. Okay, this one is something different, but okay, let's leave this one. So what else? These tensor ranks. Okay, here the main idea that we can represent, for example, tensor x, will have ones only at these positions, and these these white cubes with 0 value, so we can represent it as this one. So this tensor plus this tensor plus this tensor, which can be represented with other product of these vectors. And here we can say that using this sum of rank 1 tensors, it will be equal to 3. But if we go inside of the unfoldings, we will see that rank is equal to 2 in this case. This one. Then next. Same example, but with different values. And as the result also, here we first create, or yes, for example, create this tensor x, which is rank is equal to 3, and we can represent this one using complex values, and the rank will be equal to 2 in this case. So if we represent using real values, it is equal to 3. And if we use complex valued numbers, we can represent it just using with sum of 2 output products. Okay. And the comparison between HUSVD and singular relative composition. So this one for HUSVD, this one for CPD. One more thing here, HUSVD, these matrices are unitary matrices. For CPD, these matrices sometimes called as loading matrices. Or yes, loading matrices. And they are not unitary. And here, for HUSVD, we have a core tensor, which has values at, let's say, each point, so for all indices. And here we have a superdiagonal tensor, which has only values on its main body diagonal here. And the rest of those is equal to 0. Then this one, reveals the n ranks. So the ranks for each mode. And then we can use it for compressing data or for denoising data. What for CPD? CPD gives us the tensor rank, and also usually it is used to analyze. And here, why we use this one to analyze data, because this also we can call it as vector matrices, not the loading matrices, but vector matrices. These vector matrices has a physical significance. It is something like some features inside of our data, and we try to find these main features, which is somehow have relationships with our source data. And of course, we don't know these main features, but we can find it using canonical Polyadic decomposition. So this one is general equation for our CPD. We also see this three-way representation. Then, yes, we have this Kruskal uniqueness theorem. This one for the ranks of a tensor. I will give you that this thing has some really great ideas inside of these theorems, but it is really complicated. I will give you that some brief references. So if you want, you can check it, because usually this type of theorems I use to find new decompositions. So they always based on theorems. Okay. And I think the last step, what I want to show you here with CPD. So I show you how we can compute HOC. So as before, singular value decomposition, really easy. And here, let's go to the appendix. Here we have this approximation of our data, x0 using canonical Polyadic decomposition. But first, what we have for data model. We have our original tensor x, this one with our data, and it is corrupted with this additional noise. Usually we say that this one is complex Gaussian noise. And as a result, we receive this tensor x. And then we want to find the approximation of this original x with sub-zero here. So here you can see we can represent it as the sum of these outer products. And the main idea how we can find this type of the vectors. Let's go next. So here I introduce you alternating least squares algorithm. So you can see that we keep all the basic things. So you already know what does mean least squares. And here, this one is something like an extension for 3D case and can be used for 4D case up to RD cases. Here, the main idea as follows. So we just initialize matrices A, B, and C, just some random matrices. Then we fix B and C and calculate matrix A. So maybe let me show. Here. Not like this one. Also about how to run our product here. No. Here. Yes. Here we have different thing. So let's go step by step. We have some received tensor X. Then what we do? Not this one. Yes, this one. So let's start with initialization of B and C. So we somehow say that B is equal to the random values of this size, and C is equal to the random value of this size, and we compute A in the following way. So we compute the one-mode unfolding times this C Hadra product of B, then we take the transpose and pseudo inverse. Let's go back to one step. What we have for Hadra product is this one. For example, we have matrices A and B, and you can see that as a result, we need to multiply each value of A with all columns of B. So here we take A11 times B1, A21 times B1, etc. up to AN1 times B1. The next second column and up to the last column. So you can see we have a column-wise Kronecker product. So we can represent it with Kronecker products, and we need to collect it to one matrix in this case. Okay, let's go next. So we initialize these two values, calculate this new matrix A. Then we recalculate matrix B. So from this step, we go to this one. We use A new, keep this C as initialized one, and recalculate B using second mode. Then we find this one and go to the last step, and we need to recalculate this matrix C using new matrices A and B. And then the last step here, we found this A, B, and C, and we need to calculate this error. What we have here, we compare our received data with our estimations. So we just subtract it, and then we compute Hermitian, not Hermitian, Frobenius norm. So we can say it as Frobenius norm or higher order norm. So the main idea is here just to sum up all values. So for example, let's say that our estimates is the best fit of X, and in this one, in this case, if we sum up all of the differences between these two matrices, they should be equal to 0, because this our estimate is equal to X. So overall, let's say we'll have matrix with zeros inside of this one, and if we use Frobenius norm, we will sum up all zeros, 0, 0, 0, 0, and overall error will be 0. But what we have in general case, something like this one. So here you can see how we calculate this relative mean square error. We also divide it by the higher order norm of our data. And this one, I hope you see this. So we start with some initialization, and you can see that with the first initializations, the error is something like 1, 2, 3, 4, I think, 0.4. Then we go inside of some iterations, and for example, after maybe 10 or 12 iterations, we have an error equal to, let me check, 1, 2, 3, 4, something like 0.05. So we drop from 0.1 up to 0.05. Great, but it is just local minimum. When we go next, go next, go next, we go through this loop, go, 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 and you can see at some point we start this convergence loop from, I think, iteration number 650, maybe. We decrease our error up to something like 0.01, so 10 in the power of -2. And then we go next, and you can see at iteration 1400, we have an error equal to 10 in the power of -7. So we start with 0.1 and go up to 10 minus 7, or drop up to 10 minus 7. And here, of course, what about sizes of this tensor? It is 3 by 4 by 5, and we create this data using the sum of 3 one-mode tensors. Yes. What else here? So, the main information about ALS. So, advantages. It is really simple. So, you need to just initialize A, B, and C, and then go through this loop, recalculate at each step A, B, and C, A, B, and C, A, B, and C, and check the error between your received data and your estimation. And you go, 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 go. And the main idea here, you can set the number of iterations to stop, or you can set the threshold value of error. For example, you need just error up to 10 in the power of -5. And for example, you hit this value after 20 iterations. So you can stop just at this point, because you say, okay, this type of error is fine for me. I just use these 20 iterations. Or you can go next and maybe find better solutions. So maybe with error up to 10 in the power of -9. But of course, the main question here, how much iterations you need to hit this new lowest value of our errors. And here, these disadvantages. This alternating least squares solution can stack on local minimum, and you can see this one on this slide. So here we stack on this local minimum, and we let me see. So we calculate up to let's say 650 iterations in this local minimum. So we calculate, but we stuck on this local minimum, and then boom, and we go to some more global minimum, let's say. And here, to solve these disadvantages, which is to stack in local minimum, we can use, for example, enhancement of ALS or gradient based, or we can go to closed form solutions. So in this case, we can see here direct trilinear decomposition, or for example, this sexy algorithm, which is introduced by Professor Hart. So inside of this abbreviation, we have semi-algebraic framework for approximate canonical periodic decomposition via simultaneous matrix diagonalizations. So maybe I will show you what we have inside of this sexy algorithm. It uses the connection between HOSVD, truncated HOSVD, and canonical periodic decomposition. And this one is not iterative algorithm; it is closed form. So you need to calculate only once, and you will get great results. So something like this one. So maybe what time? So maybe we will write down this alternating least squares solution in the next lecture. So how we do this thing, how we go through these iterations, and then for today we will stop at this point. So let me see what else we have here. So yes, for example, we can go inside of this semi-algebraic framework. I will show you just main ideas here, because it is really huge algorithm. Here they use different relationships between HOSVD and CPD. And maybe also I can show you the block term decomposition also. So let's stop here. I will stop also the recording. So goodbye. Stop recording.
Thank you. Goodbye.
So yes, thank you. Goodbye. Have a great evening.